Hi, everyone. I'm going to quickly try to give you a presentation that I've given to the public on a few occasions in the past. And the reason why I'm giving this presentation is that I tell a little bit of my personal story as a way to try and uh, help people think about the enormous amount of change that we've seen in terms of greenhouse gas concentrations, in addition to the levels of temperature rise and weather effects, and the long-term average of temperature and weather effects creates some very worrying conditions and trends. So without further ado, I generally introduce people to my research program because oftentimes people ask me how much volcanoes contribute to emissions of CO2. So that's something that I'll touch on in this presentation. I also talk about how my work in the subarctic and the subantarctic has allowed me to witness glaciers retreating at an enormous pace over the course of 30 years. I also work with archaeologists and paleoecologists, which gives me an opportunity to hear from them about how they see a diminishment of cold water fish species and how they see people in prehistoric times reacting to changes in their environment, including sea level rise and changing ecosystem. So I grew up in Wyoming, little sunny Wyoming there. You can see me climbing out of the swimming pool. Um, and when we talk about carbon dioxide in the atmosphere, I realized just in the last year or two that I was born at a really interesting time with regards to carbon dioxide and temperature change. So the green arrow shows you what the concentration of carbon dioxide was in terms of parts per million. Now, I'll talk about parts per million and give you an analogy to that in some upcoming slides. The other interesting thing about when I was born is it was very nearly at the benchmark for the 20th century when people said, hey, let's consider this our average temperature. And so on the left-hand side of the lower panel, you'll see the temperature says 0. Now, that does not mean the average global temperature is 0 or freezing. No, it means that we're going to be comparing our current and future temperatures to that baseline. And if you look at that lower graph, you see that the pink line, which is the average of the annual temperature measurements at every weather station and city that reports in the world, you see that that line has a lot of jagged spikes. And that can make it hard to see what the long-term climate average is. So superimposed on that yearly average is a blue line. And that blue line is created by taking 5 years of temperature data and averaging it. So for example, to get the number on the blue line for 1900, they would take the numbers for 2.5 years prior to that, and 2.5 years beyond 1900. And they would average the 5 years of data and plot that right at 1900. And then they would go to 1901 and they would average 2.5 years previous and 2.5 years beyond 1901, and they'd get their average. So sometimes we call this a moving average or a smoothed curve because it is that average. Okay, let's move on to the next panel. Okay, so I like to tell people what is a part per million, because this makes it a little bit easier to see how powerful the effect is of a small amount of greenhouse gas addition, as well as it helps us see why it's so difficult to deal with this issue. So in the lower panel, we have an Olympic-sized swimming pool. And if we took 100 tablespoons of sugar or salt, and we dumped those 100 tablespoons into the swimming pool full of water, we would have added 2 parts per million of sugar to our water. Okay, so we're thinking about a trace amount compared to our overall water in the swimming pool. All right, well, I heard a little bit about global warming when I was in high school, but I grew up in a very Republican family, a very conservative ranching family. And so there was a lot of skepticism about global warming. I then went to college at Colorado College, and I heard a little bit more about global warming and some of the evidence for that. But by the time I went to University of Wyoming for my master's degree, which is indicated by the yellow arrow, I was definitely hearing that most scientists were becoming really convinced. So after I finished my master's, I started my PhD at MIT. And while I was there in the Department of Earth, Atmospheric, and Planetary Sciences, uh, all the visiting lecturers were talking about climate change. And at that point, people started to realize that the climate system won't simply warm. There will be a lot of warming, but the effects will include more precipitation in some locations, whereas it'll be drought in other locations, and there'll be greater storminess in some locations. And so, really, it was at that time when I was doing my PhD that people started talking about climate change instead of solely climate warming. All right, so during my lifetime, carbon dioxide has increased by 126% in the atmosphere. And I'm going to show you what this looks like. Still, on this image, the green arrow is the time when I was born. The yellow arrow is when I did my master's. And the orange arrow is when I finished my PhD. Now, a lot of times people ask me why this black curve is jagged like this. And this curve is very famous. It's called the Keeling curve because Keeling was the man who had the idea to set up an observatory to measure carbon dioxide at Mauna Loa, Hawaii. Now, this was brilliant. Here's why. Hawaii is far away from any smokestacks. If you wanted to measure global CO2 and you put your monitoring system in Los Angeles, you're going to have a very skewed perspective. On the other hand, if you put your measuring system in the middle of the Sahara Desert, you might have a different skewed perspective. The nice thing about Hawaii is it's in the middle of the ocean. There are always air currents that are helping mix the atmosphere well. And so by the time the atmosphere that's being measured gets to the Mauna Loa Observatory, it has mixed all the outputs from all the nations of the Northern Hemisphere. Okay, well, I eventually had an academic job in Wisconsin. Then I was a research scientist in Belgium. Then I was a tenure track professor at Kansas State University. But then I had the opportunity to move to Whitman, and it's near volcanoes. It had an opportunity for my partner and lots of places to go play in the outdoors. And we've been so happy here. So when I was hired at Whitman in 2006, my oldest son was a year and a half old, and my second son was born in Walla Walla. So when I taught environmental geology in the spring of 2007, the amount of CO2 in the atmosphere was about 382 parts per million. Now, that was already far above the amount when I was born, but I hadn't really been paying attention to the numbers of the atmospheric CO2 concentration. Well, time marches onward. The last time I taught environmental geology in 2015, you can see how high the CO2 levels were. And then in 2018, when I taught the lab for environmental geology, it was off the charts. I had to create a new plot the last time I taught environmental geology. And we're even above these numbers now. So this is what a lifetime, my lifetime of carbon dioxide concentration looks like. And we should be thinking, well, I am thinking, what is the CO2 going to be like over my kid's lifetime? Okay, well, how do we know that this is unusual? And how do we know that this might be a cause for concern? And what we use is ice core data. Scientists have gone to Greenland and Antarctica and used a generator to power a drill, and they have recovered 3,500 meters, more than 11,000 feet of ice in a single location. And they take these cores out in smaller pieces. But of course, what happens is each year the snow falls, it traps some air in between the snow. And then as that snow compacts and recrystallizes into ice, air bubbles get trapped. And those air bubbles extend back hundreds of thousands of years in terms of the record of these ice cores. And here's an ice core at the upper left, and you'll notice that it's got these sort of rings looks, uh, the appearance of rings as you go along the ice core. And this is the annual yearly cycle that we're able to look at. And then, of course, you see a really dark layer in the ice, and that's where there was a volcanic eruption, and that is volcanic ash. And so scientists actually work in giant freezers to slice segments out of these ice cores. So at the lower right, you see they use a large part of each annual deposit to determine what the trapped gas type and abundance is. They also perform other kinds of chemical measurements. They take a look at isotopes, and then we always archive a substantial portion of these cores so that the data can be verified or alternative kinds of measurements can be made in the future. And so when we look at the ice core data on this graph, 0 at the far right is today. And the ice core data stretch back 800,000 years. And you can see how the amount of carbon dioxide goes up and down in a pattern that people have linked to the production of ice and periods when we had more ice, deeper winters, glacial periods. And those glacial periods, excuse me, correspond with times when the carbon dioxide levels are low. And the warm periods or the interglacials are periods when the CO2 concentrations in the ice core bubbles are high. And prior to the modern era of using coal, natural gas, and petroleum for energy and heat sources, the highest concentration of carbon dioxide was only 300 parts per million. So keep in mind that we've had a recent ice age, but if we look at where we are today, boom, there's my experience. And so the problem is primarily that we are at such high levels now. But another reason we are concerned is because how quickly these levels have been reached. In 50 years, we've seen CO2 concentrations rise, and in the past, it would have taken hundreds or thousands of years for a similar rise in concentration. So we're at a really high rate of changing the CO2 levels in our atmosphere. Okay, well, if we're going to try and tackle this problem, we need political will to do so, which means we need the public to understand that this is a problem and to want to do something about it. Well, the good news is that the Yale University has done a survey where they have collected data from almost every county in the United States, county by county. It's really an astonishing concept and an astonishing amount of work. So published in 2018, and there has been a recent update, you can see that when asked, did adults think global warming is happening? As of 2018, the bar at the bottom says, on average, all those counties together, 70% of voting adults, or at least of the age to vote, 70% of adults were convinced that global warming is happening. That's going to help us tackle this problem. When the public in those counties was asked, do you believe that global warming is caused mostly by human activities? Only 57% of people agreed with that statement. It's still more than half, but not quite as great. And 30% of people, approximately, believe that natural changes are causing this. Well, the update that was released in November of 2019 shows that more and more people are convinced that global warming is happening and that it's caused by human activities. And notice that 62% of people agree that global warming is affecting short-term weather. So, as a nation, we are mostly convinced. Now, are we worried? What do we think about this? In terms of risk perception, when asked if people were worried about global warming, 61% of people are worried. And they're worried that global warming will hurt plants and animals, and that it will hurt future generations, and that it will harm people in developing countries. So we're convinced that there's some risk involved with this global climate change. So we are mostly convinced and we are worried. Now, when you ask, will global warming harm people in the US, notice only 58% of people agreed that global warming would help us in this nation. And fewer people thought that it would hurt them personally or that it was already harming people in the US. Now, remember, we had the Camp Fire take place after this survey, and we had all the flooding in the Midwest and Nebraska, and we've had increased number of tornadoes really early in the season and large hurricanes like in Puerto Rico. So actually, these data, even though they're 2 years old, less than 2 years old, are already out of date. So what most people think is that there is a serious problem. Is human energy choice really causing global climate change? What about natural factors? Well, I love this simulation by the Bloomberg magazine because it really captures what we're thinking here. All right. Notice that again, we're looking at the average temperature from 1880 to 1910 on the left axis. And because this is for the general American population, now we're talking about degrees Fahrenheit instead of degrees centigrade. And we're going to be looking at the record from 1880 on the left until 2014. And that's because 1880 is about when reliable temperature data started being recorded. Okay, so this is the observed measured land ocean temperature. Could Earth's orbit explain how Earth's temperature goes up? Well, this blue line has just plotted changes in Earth's orbit. That would be the kind of thing that we talk about if people mention Milankovitch cycles. And what you can see is there's a little wobble, but that wobble hasn't really contributed to a change in temperature. Now, the blue line is the average, and you can see some little stippled dots that show you the confidence envelope. In other words, 95% of all estimates fall within the shaded region. Well, if it's not Earth's orbit, what else could it be? Could it be that the sun has changed, having greater or lesser amounts of output over time? And what we see is from records of sunspot activity and luminosity, we do not see an increase in the power or the energy reaching the earth from the sun. All right. How about volcanoes, my favorite? Okay, there's no way that you can take a look at this curve and see that volcanoes are increasing their CO2 output in the same way that we see temperature increasing. However, there is a bit of an interesting correlation that I'd like to point out to you. Notice that about right here where I'm moving the cursor, I hope you can see, it's relatively recent, 1993. Global temperature has a dip, and that dip matches the predicted temperature effect of a huge eruption. This is the eruption of Mount Pinatubo in the Philippines, which was the second largest eruption in the 20th century. Now, of course, the amount of ash and CO2 went way, way up, and that blocked the sun's rays from reaching the earth. And that's why a large eruption on this graph creates a decrease in temperature. So we have a large dip associated with Mount Pinatubo. And before that, in 1964, El Chichon had a very large eruption. Before that, Agung in Indonesia had a large eruption. And we can trace this back. So volcanoes do put a lot of material into the atmosphere, but it tends to cause cooling. And the other thing is that we can see that these are short-lived effects. They act for a couple to up to 3 to 5 years at most on the global temperature. Now, we could have an even larger, more devastating eruption, but we don't want to go there. So if we combine all of these natural factors together, does that explain the observed rise in temperature? And the answer is no. So let's take a look at what people have done. We've cut down forests so we can have different kinds of agricultural production. We might want to graze cattle or have crops instead of forests. But forests, being dark green, actually absorb a lot of the sun's energy, right? That's the whole purpose of a leaf. And when we cut down forests, very often the land that's left behind reflects sunlight more than it would have before. And so we see temperature due to land use changes actually would have decreased. What about ozone pollution? Well, there's a slight increase in temperature that could be attributed to ozone, but it's nowhere near the observed temperature increase. How about aerosols from coal burning power plant? Well, these aerosols actually block sunlight from making it to the Earth's surface, so they would cause cooling. But as the caption says, they also can cause acid rain. How about greenhouse gases? When we look at the concentration of greenhouse gases, in fact, that rises even more than our observed temperature. Our CO2 levels are 40% higher than they were before the Industrial Revolution. What if we combine all of these things together? If we combine all the human factors, it matches our observed temperature change almost perfectly. And if we add in the natural factors, we get an excellent match because those volcanic eruptions help us understand some of the dips in our temperature record. So when we combine looking at natural factors and human factors, we can understand how our temperature globally has been going up. And we see that the biggest contributor is the increasing output of greenhouse gases.